Hello everyone. Today I'll be discussing one of the very important topic called OFDM, that is orthogonal frequency division multiplexing. It has been used in cellular technology very widely in LTE 4G, 5G, 6G, and in WLAN systems. OFDM was first used by 802.11a, which is the successor of 802.11b. 11b used DSS, TSSS, that is direct sequence spread spectrum. 11a used OFDM, or the multi-carrier modulation, for the first time, followed by 11g, 11n, 11EC, and 11AX. 11AX first time used OFDM-A. So I have an experiment next which uses OFDM. So before going into the OFDM experiment, I thought there is a need for explaining what is an OFDM, uh, what is the use of it in wireless communication. So I was thinking like how to explain this particular topic, because there is n number of resources which is available online. You can also find video lectures, so many materials, blogs which is being written on OFDM. So actually I was very confused. Uh, I was just thinking like how this particular topic has to be taught, because I know the audience or the people who are listening, they are like, they have diverse interest, and maybe they have already studied wireless communication and they know what is OFDM is, or they might be in lower semesters still not doing any course on wireless communication. So I thought, okay, let me explain in my own way, keeping things simpler and assuming that the listener do not know anything about OFDM. So then I came up with a way, okay, let me go through the notes which I have done in the, maybe probably this I have done in first year or second year of my PhD. I was trying to recollect or understand or trying to relate the concepts of feeding with OFDM, and I have written some notes which is maybe 3 or 4 years older. So if when you scroll down, the font size is very much varying. Sorry for that, but what my objective is to uh, explain this particular topic in a way so that at the end of this discussion, you should be able to know at least the basics of OFDM, like why is that OFDM very important and it's a buzzword everywhere. So let me start with this topic. And yeah, there are some math equations which I have written, but if you can understand the math behind or the signal processing, it is fine. If you do not understand, that is okay. I mean, try at least understanding the basic concepts. That is fine. So here in this particular notes, what I'm trying to relate this OFDM with fading. So to start with, I have written an equation. This equation represents the time varying channel, wireless channel. So which is represented in terms of LTAP filter. So here h of t comma tau is, t represents time varying. Tau is a variable in order to indicate or represent the various delays. So if you can remember in the very first experiment when I was discussing about the multipath propagation in the wireless communication, I have talked about this. So to repeat, wireless channel is modeled as a multipath channel, because when you transmit a signal at the transmitter, at the receiver you don't get a single signal, or the signal is transmitted or propagated through multiple paths because of the surrounding wireless environment, because you are transmitting the signal over air. So here you have so many obstacles around, right? If it is an indoor, you have walls, fans, door, etc. If it's an outdoor, you get to see trees, buildings, etc. So the energy which is being transmitted at the transmitter is received at the receiver, not only through a single path, but the same signal undergoes reflection, scattering, etc., and gets reflected through an obstacle and gets received at the receiver. So one thing is you have multiple paths, and the, the signal, when it is traversing through multiple paths, the distance traveled by each of these signal component varies. Therefore, each of the path or the multipath component arrives at different time instances at the receiver. So this we technically call it as delay. Say first path arrived after time tau 1, the second path arrived at time tau 2 like that. So that's why it's called multi path channel, or uh, the signal which is being received through the multiple path. So now this equation represent, you have L taps here, assuming L tap filter. So this is a attenuation undergoing by the particular path. Then this is a phase component. So when there is also phase difference between the signals which is being received at the receiver, right? And tau n is the delay. So tau minus tau n, negative sign here indicates that there is a delay in the signal. So what is h of t comma tau? We tell it as an impulse response of a channel at time t for an impulse launched into the channel tau seconds earlier. Meaning now you are receiving the output at the channel, but you have given the impulse signal tau seconds before. So that is the definition of impulse response. So if the channel impulse response has multiple taps, then the channel is frequency selective. So ideally speaking, so if you go for wired channel and all, you have a single path, then impulse response is just an impulse. Okay, then what is the Fourier transform of an impulse? It's a constant signal. Then h of f is flat over frequency, then it is called frequency independent. It's called frequency flat. But when you have multiple taps, h of t is no more a single impulse. So we have seen in first experiment where we saw what is the channel impulse response of a indoor model D channel. We saw multiple impulses, right, at various sitting at various delay points. So h of f is dependent on frequency. It is not flat. Instead, when you plot h of f versus f, it is a function of frequency. Then we call the channel as frequency selective channel. So here comes an important term called delay spread. So what is a delay spread? So I'm just representing this h of t comma tau versus tau. So at different delay points, tau naught, tau 1, tau L, and minus 1 like that. So the signal time difference between the arrival of the first multipath component at the receiver and the last multipath component at the receiver, there is some time difference, right? So that is called associated with a single transmitted pulse. Then this is called delay spread. If the channel is time invariant, okay, this mobility thing, let's not discuss now. So I just want to focus on the delay spread thing. So this delay spread, the coherence bandwidth of the channel is inversely proportional to the delay spread. So what is a coherence bandwidth? It's a range of frequencies for over the channel can be considered as flat, or in other words, if the signal, we know when you transmit across a channel, the signal has different frequency components, right? If the signal bandwidth is much lower than the coherence bandwidth of the channel. So coherence bandwidth is a property of a channel. When you have a signal whose bandwidth is less than the coherence bandwidth of the channel, meaning all the frequency components of the transmitted signal undergo same amount of attenuation and phase shift, then it is called as frequency flat fading, meaning the signal is going to see the frequency flat channel. So here, this is an example. So you have a signal bandwidth B. I'm representing coherence bandwidth of a channel BC. And that is dependent on what? It is a channel property and it is dependent on the delay spread. If the delay spread increases, the coherence bandwidth of the channel decreases and it is said to be more and more frequency selective. Let BC be the coherence bandwidth of the channel and B be the signal bandwidth. If BC is much, much lesser than BC, then the signal sees almost a frequency or experiences a frequency flat channel. The channel might be frequency selective, but the signal bandwidth is much lower than the coherence bandwidth of the channel. So for this signal, the channel appears to be more or less flat. So then it experiences frequency flat fading. That is what we tell. Or the signal is called, or the signal sees a frequency flat channel. But if the signal bandwidth is in the order of BC, right? If B is nearly equal to BC or B greater than BC, then the signal experiences frequency selective fading. So this is very important concept. So in this is pictorially shown here. The blue thing, say this is the signal bandwidth is much greater than BC. Obviously, if you see here, the different frequency components of the signal, you see h of f is not flat here. So they experience different amount of attenuation and frequency distortion. So now, this is something you should remember. Multipath means you have signal reception more than one path or multiple paths, say L paths. What is delay spread? The time difference between the component which arrived at the end and the signal path component which arrived at the first. So that is called delay spread. And the signal the coherence bandwidth of the channel, it's a property of the channel. It is inversely proportional to TD. As TD increases, meaning you have more and more paths, right? Then TD increases. As TD increases, BC decreases, meaning the coherence bandwidth of the channel becomes more and more narrower. Then the channel is called as frequency selective. Of course, again, whenever you tell the frequency select channel is frequency selective, it is always referred with the signal bandwidth. BC might be very small, right? But if B is less than BC, then signal C is frequency selective channel. If B is much greater than BC, meaning B is signal bandwidth much greater than BC, then the signal C is frequency selective channel. Sorry, in this case, if B is less than BC, then the signal C is frequency flat channel. So always when you define what is frequency selective, whether this channel is frequency selective or frequency flat, always you should consider or take the reference of signal bandwidth, how you should compare the signal bandwidth with the coherence bandwidth. But in general, I tell when TD increases, coherence bandwidth of the channel decreases. If you want to illustrate the effect of this delay spread in time domain, say this I'm characterizing the channel. So when you have, say you have two pulses here, you're transmitting a pulse with a signaling interval of TS, and that is equal to 1 over bandwidth. Typically, TS will be greater or equal to 1 over B. I have chosen TS equal to 1 over B. And at the reception, what happens because of the multiple pass, the first pulse is not only received or you receive here, there is also due to the additional pass, you are going to receive the copy of the same signal. So this blue thing is a copy of the same signal you have received. What happens if TD increases? So you have sent one pulse. Because TD is larger, so you're receiving the same pulse. Pulse 1 first copy. This is a pulse 1 second copy. The pulse 1 third copy. If you send another signal, say yellow signal here, what is happening? The yellow signal is getting interfered with the pulses, the copies of the pulses which is being received. So each of the different multipath components can be resolved, but however, this multiple components interfere with the subsequently transmitted pulses. So this was the pulse 2. The copies of the pulse 1 is getting interfered with the pulse 2 in time domain. So this is called intersymbol interference. So if this happens, it becomes very difficult to recover the pulse at the transmitted pulse at the receiver. So how to overcome ISI? So in a single carrier system, they use equalizer. Another efficient way of overcoming this ISI in multi-carrier system is use of OFDM. So this is computationally less complex and more efficient. So this is the motivation for OFDM. So next we will see what an OFDM is in detail. But what is the need for OFDM? Typically due to the multipath propagation, the nature of the signal in the wireless environment, what happens? The signal arrives at different time instances, because of which there is a delay spread, and the symbol interfere with each other, or the first transmitted pulse or the copies of the transmitted pulse get interfered with the neighboring pulses, resulting in ISI. So one way to overcome this ISI is OFDM. So going back to the OFDM nodes, yeah, again here there is the change in font size. I'll accordingly adjust it. Okay, so here we see the basics of OFDM. I've tried to explain in a different way so that it is easy for understanding. So when you have a single carrier system, what does that mean? So you have a carrier. So each symbol is transmitted. It occupies the entire bandwidth. So this is a frequency axis. This is a time axis. So whenever you are sending a symbol 1, it is occupying the complete bandwidth like this. Okay. Second symbol you transmit after time t. T is a signaling interval, and I have taken t equal to 1 over b. Second symbol again occupies complete bandwidth. Like this, every time when you send a symbol, the symbol is occupying complete bandwidth. So what is the symbol rate here? I have sent one symbol in time interval 1 by b. So I can tell symbol rate is simply b. Okay. So here what I have written serially, in the sense I'm sending symbols one after the other. So but in every time slot t equal to 1 over b, I'm sending only one symbol. So it is 1 by 1 over b. So symbol rate is b. That is b symbols per second. So now I've taken some examples. Here B, say B is equal to 20 megahertz. So the simple time is 0.05 microseconds. In an indoor model D, 11AX channel, we have done this experiment in experiment 1. And we saw that the delay spread, maximum delay spread is 390 nanoseconds, right? So here the symbol time is much, much less than T. Symbol time, so this is 0.39 microseconds. This is 0.05. Symbol time is much, much less than D. And the signal bandwidth is much, much greater than BC. So this leads to ISI, right? If the 11AX model D, in practice, OFDM is used. Assume there is no OFDM and you have transmitted using a single carrier. Then what happens? Because the symbol time is very small compared to the delay spread, this will lead to ISI. So in order to overcome this ISI, what is done? They divide the channel, divide the 20 megahertz channel into number of subbands so that it is narrow enough, so that it does not face any ISI. So each sub bandwidth or reduced bandwidth, I'm calling it as delta F. And the delta F is designed such that it is less than BC. So when you have bandwidth of B hertz, when I divide it into a number of subcarriers or subbands, delta F is equal to B by N. So for the same example, in 11AX, in practice, the 20 megahertz bandwidth is divided into multiple 256 subcarriers. And when you calculate, you have the sub bandwidth as 78.125 kilohertz. Okay. And over this, every subcarrier, the symbol is transmitted. So OFDM symbol time is nothing but 1 over delta F. It is N times B. Okay. Earlier in a single carrier, what was the symbol time? Symbol time is simply 1 over B. But in OFDM, it is N times 1 over B. So symbol time is increased by N. So symbol time is 12.8 microseconds. And there is also a cyclic prefix which is added. We will see why the cyclic prefix is required, but just I'm saying, comparing TS with TD here. So TS is 3.2 microseconds. So the total OFDM symbol time is 16 microseconds, which is much, much greater than the delay spread. For channel model D, the delay spread is 0.39 microseconds, and 16 microseconds is much greater than 0.39 microsecond. So here, yeah, the same thing I'm trying to interpret in a single carrier. You're transmitting one symbol over one carrier over the bandwidth B. The signal interval is 1 by B. Here, this is the time axis, this is the channel axis, frequency axis. The entire bandwidth is divided into number of subcarriers, N subcarriers, and delta F is the bandwidth around the subcarrier. So this is at the center. Okay, so delta F is the bandwidth or the subband for each subcarrier, and the symbol is transmitted over that. So what is the time duration then? Time required is N times 1 by B. So you do parallel transmission, but the time required for transmission of all these N symbols over each of these subcarrier is N times 1 by B. So what is the symbol rate? Do we gain in symbol rate? No, this is because in single carrier, you're transmitting one symbol in 1 by B time. Here, no doubt you're transmitting N symbols parallelly, but the time required is increased because here the bandwidth given was larger. The time was small, but here you have decreased the bandwidth, right? So the time required is increased by N times. So symbol rate is you're transmitting N symbols, but in N by B times. So the bandwidth or the symbol rate is same. You don't gain anything in symbol rate. But what is the advantage? Then why did we go for OFDM? Why did we do this? Why did we divide the entire bandwidth into N subbands or subcarriers? So for this, we will go through further notes. So the wideband channel, I'm calling it as frequency selective channel with ISI. So here the bandwidth is B. The output symbol at any sampling instant is given by this. Here I modeled the filter, the channel as a LTAF filter. So Y of n is convolution between the input X of n and H of n channel impulse response with additive white Gaussian noise. So channel is modeled as a LTAF filter. Again, if you have learned signals and systems, you can understand this. But if you're not aware of the math or the signals and systems required for this in understanding this wireless communication and all, that is okay. Try to understand conceptually. So here the output of a signal for any LTI system can be written like this. So I assume the input signal is 0 for n less than or equal to 0, then I can compute what is y of 1, simply substituting n equal to 1. So I can write these equations. I don't want to go into the details. What I just want to tell is the output symbol depends upon the current input symbol, right? If you go to any time, for example, here also y of n depends on x of n, y of 2 depends on x of 2, but also it depends on x of 1. Y of L depends on X of L, but also depends on the previous samples, L minus 1, L minus 2, etc. So at any time, say at the nth time instant, Y of N is what happening. It is dependent on the current input symbol X of N. This is desired, but it's also depending on X of N minus 1, X of N minus 2, up to X of N minus of L minus 1. So this is depending on the previous L minus 1 input symbols. This is not desirable. This is called ISI. So this somehow we need to get rid of this, because it becomes at the receiver it is becomes difficult to decode or to recover x of n from y of n. Ideally speaking, I want only this term. I do not want this term. But in practice, because of the multiple tabs or multipath propagation, there is ISI. So for OFDM, so I told there is a CP. Let's assume we do not know what a cyclic prefix. So without introducing that cyclic prefix, let me try what an OFDM does. So bits are taken, the bits are mapped to the constellation. So bit to symbol mapper. So you have here the constellation symbols. It can be from MPSK or MQAM, etc. So serial to parallel conversion is done so that you have at every here at the output you have one constellation symbol x of 0, x of 1, like that. So now I take endpoint I50 on this. Okay, you will get complex samples. Then this is again parallel to serial conversion you do and transmit over the channel, right? So this you might have come across whenever you see what an OFDM is. This is a block diagram. But if you want to know the history, why I should go for I50, all this stuff, I would recommend you to listen to Aditya K. Jagannathan, a course on advanced wireless communication, where he covers what is a multi-carrier modulation to start with, and what is the disadvantage of multi-carrier modulation, and what is an OFDM. To tell in eye level, see, when you have multi-carrier modulation, you require a bank of n modulators and demodulators at the receiver. When I tell modulator, you need a carrier, local oscillator at the transmitter. And again, at the receiver, you need to have the same oscillator, meaning the frequency and the phase of the oscillator has to match to the local oscillator which is being used at the transmitter. So it is very difficult in practice. And again, if you have bank of n modulators and demodulators, so it is very computationally complex. And in order to overcome that, OFDM is being used. It is found through one of the findings in 1971 that when you take a multi-carrier signal, a composite signal, and you do sampling on that, the sampled signal is nothing but the I50 of the complex constellation symbols. This was a discovery made in 1971, which led to OFDM. So here also what we are doing, we are simply taking I50 of the complex constellation symbol in order to get the complex samples. So this was the motivation for OFDM. So I would recommend to listen to those lecture series in order to get a deep understanding of OFDM. Here the objective is just to try to tell OFDM in a high level. So here you have a constellation symbols. You do endpoint I50. So here basically I'm seeing the constellation symbols as a frequency domain view. So when you take I50, you get the time domain samples. So they're also complex samples. You're going to serially transmit it over the channel. At the reception, I get those in received complex samples. This is with noise, so I have written here as tilde. Here there is no tilde, so this is corrupted with noise. Again, you do serial to parallel conversion. Now you do endpoint F50, right? Then you get the recovered constellation symbols. Then you do parallel to serial conversion. So this is the block diagram of OFDM. One thing I have not done is I'm not told anything about CP. So this is without CP. CP is cyclic prefix. So what happens in that case? See, ideally, this transmitted constellation symbols and whatever you receive here after recovery, yeah, this one, ideally should be equal to this, whatever is being transmitted, right? If there is no noise and you assume the channel estimation is perfect, then this x tilde of key, whatever you recover, should be equal to whatever was transmitted. So let's try to understand OFDM. What are the sequence of steps which is being done? So at the transmitting end, what I told, you have a complex constellation symbols. Either it belongs to MPSK or MQAM. So the frequency domain view, now you approach endpoint I50. So this is something like you're loading the constellation symbols onto N subcarriers. So you have the time domain samples. You have transmitted them in parallel across the multiple subcarriers, right? Then at the receiver again, you get these. You do endpoint I50. You have got the recovered constellation symbols. Ideally speaking, this must be X tilde. Capital X tilde must be equal to capital X. Ideally, meaning no noise. And if you have estimated the channel perfectly. So what happens due to the multi-tap nature of the channel or due to the multipath propagation of the wireless environment, without cyclic prefix, what is the effect? So again here, the frequency selective channel is modeled as a LTAP filter. So if you see, you have L minus 0 to L minus 1. So it's a LTAP filter, H of n. It's not a single impulse, but you have, it means this is the first path, this is the second path, this is the last path, which is being received at the receiver after some delay. So consider two FDM symbols for simplicity. To understand what is the need for cyclic prefix. So this is the current OFDM symbol. So when I tell OFDM symbol, it means the samples, the complex samples which I have got after performing I50 on the complex constellation symbols. So this one, x0 to xn minus 1, this is called one OFDM symbol. And one more point to note, typically when I tell endpoint filter, endpoint I50 or endpoint F50, so this I50 or F50 is a fast Fourier transform, right? The way to realize DFT very fast. So n is typically in the order of like 2 to the power 2 to power 4, that is 64 or 256. It will be in that order so that the computation happens faster. And yeah, coming back to this, so you have 0 to n minus 1 as a current OFDM symbol, and previous OFDM symbol also has n samples. Just to distinguish this from this, I'm representing as x tilde to x tilde of n minus 1. So I'll say I pass these two symbols through frequency selective channel. What is the effect? So again, I use that equation where y of n is written as there's a convolution between h of n and x of n. I don't know whether I have, yeah, this equation. It is simple. So n equal to 1, you can expand this equation, right? L equal to 0, what is it? For y of n, h of 0, x of n plus h of 1, x of n minus 1 plus h of 2, x of n minus 2 plus so on up to h of capital L minus 1, x of capital L minus n minus capital of, sorry, the last part is h of capital L minus 1 into x of n minus of capital L minus 1. So you need to expand this. I think I haven't done that. After that, you need to substitute n equal to 0, 1, 2 like that. So use that equation, and if you can solve this, you get y of 0, the first complex sample is this, the second as this. And if you see, ideally y of 0 has to depend on x of 0, but it is depending on the previous sample. So here previous sample was x tilde and this one. And again, other samples also. Ideally, y of 1 has to depend only on x of n, but there are previous samples. So previous to this was x of 0, x tilde n minus 1. So all that is coming to picture. If you go to y of L minus 1th sample, I think here there is no interference. Yeah, there is no interference because it is, yeah, still there is interference, but there is no interference from the previous OFDM symbol. So y of L minus 1 is what? X of L minus 1, x of L minus 2. Where is that? Yeah, x of L minus 1, x of L minus 2. There is interference, but between the samples of the same OFDM symbols. Okay, if you go to this. So same thing I've written, y of 0 has interference from L minus 1 samples of previous OFDM symbol. Y of 1 has the number of interferences decreasing. When you go to y of L minus 2, it has interference from one sample of the previous OFDM symbol. That is, it will have an interference from this thing. Okay, when you go for y of L minus, there is an interference, but not corresponding to the previous OFDM symbol. The last y of L minus 1 sample has interference from the samples of the same OFDM symbol or the current OFDM symbol. So that is I have written there is no interference from the previous OFDM symbol. Okay. So the first L-1 samples undergoes symbol interference. There is interference from the previous OFDM symbol. The interference is from the previous OFDM symbol consisting of n samples. So the OFDM symbol time is increased. There is an effect of ISI in the initial part of the residual OF symbol. So this is important. So no doubt in OFDM, what we did, we divided the entire bandwidth into small subbands. This in turn, what happened? The symbol time increased by the same factor. So uh, B by N was delta F, but now the symbol interval is increased by a factor N. But still, in the initial part of the OFDM symbol, we have interference, right? Y of 0 is interfered, Y of 1 has interference, Y of L-1 has no interference. So this Y of 0 to Y of L-2, almost L-1 samples are still experience interference. So what is done? So in order to overcome, we do the cyclic prefix, right? So because here y of 0 to y of L-1 had interference from what? Had an interference from previous OFDM symbol. So what do I do? So natural way is, okay, what this is the previous OFDM symbol. There is an interference for first L-1 samples from the previous OFDM symbols. So one natural way is, okay, instead of what do I do is simply cyclic prefix. I'll take L-1 samples from the current OFDM symbol. Same thing I place it before. This is done for every OFDM symbol. So for example, this OFDM symbol also in practice, you cyclic prefix the last L-1 samples and place it at the beginning. So that is the cyclic prefix. So input symbol and the channel impulse response, right? So we can fast way you can compute the circular convolution, and when you take a DFT, we know circular convolution in frequency domain is simply becomes multiplication of the transform when you take DFT. So DFT of h of n convolved with x of n is simply DFT of h of n into DFT of x of n. So this is flat fading. So in frequency domain, it is seeing flat fading. So the output at the kth subcarrier is equal to the symbol which is transmitted on the kth subcarrier. Symbol is a constellation symbol, and h of k is a channel coefficient at the kth subcarrier. So the wideband frequency selective channel is now converted into a narrowband flat feeding channel, right, using multi-carrier modulation and the addition of CP. So this is the advantage of OFDM. You have low computational complexity because I'm using I50 at the transmitter and I50 at the receiver. It is converting the frequency selective wideband channel into flat fading channel. So here I'm not using any bank of modulators or demodulators, like using local oscillator, bank of local oscillators at the transmitter and the similar oscillators at the receiver. Simply I'm doing F50 at the transmitter and F50 at the receiver. And I'm doing cyclic prefix in order to remove the effect of ISI between two adjacent symbols. Okay, though you add cyclic prefix, still you, as I told, as we saw or discussed, there is intersymbol interference, but not with the adjacent OFDM symbol, but within the samples of the same OFDM symbol. So what to do? Simple. See, this is the same thing, only thing changes addition of CP, right? And I know I have added CP. I've now avoided ISI from the previous OFDM symbol, but still there is an ISI from the samples of the same OFDM symbol. How many samples are getting? I know L-1 samples are getting affected. So simply remove that. So before further processing at the receiver end, as soon as you get the symbol, all right, you are going to avoid or remove the CP. L-1 samples are removed and further samples are processed, right? Further samples are processed. You do endpoint I50, sorry, endpoint I50 at the receiver, you get the the constellation symbols which is being transmitted, right? So this is the basic idea of OFDM. So what is it? Simply to summarize, wireless channel, multipath propagation. When you have multipath propagation, signal components arrive at various delays, because of which there is a delay spread. When there is a delay spread, there is something called coherence bandwidth. The coherence bandwidth of the channel is inversely proportional to the delay spread. When delay spread increases, the coherence bandwidth of the channel decreases. But when you pass a signal through this channel, okay, which has some coherence bandwidth BC, whether the signal is narrowband channel or frequency selective or narrowband or frequency flat channel or frequency selective channel entirely depends upon the signal bandwidth. If the signal bandwidth is very much lesser than the coherence bandwidth of the channel, then the signal sees frequency flat fading. If the signal bandwidth is greater or relatively comparable to the coherence bandwidth of the channel, then it sees frequency selective channel, right? And what is this OFDM? OFDM, we are actually, what we are doing, we are taking the bandwidth and dividing into smaller bandwidths, okay? And so that the delta F is B by N, right? And we are trying to transmit each of the constellation symbol over this subcarrier. And without adding CP, what happened? And or in doing this process, what happened? TS, the symbol time, became much larger when compared to TD. In single carrier, TS was simply 1 over B. When you go for OFDM, TS becomes N times 1 by B, right? TS must be greater than TD. That is a desirable thing. So TS, if it is much, much greater than TD, then the signal becomes more flat. And one more thing we saw was without CP, there was ISI between OFDM symbols. We added CP. Still, there was an ISI. We don't call it as ISI, we call it as ICI, okay, inter-carrier modulation, because there is a interference between the subcarriers, okay, between the subcarriers within the same OFDM symbol. So it is called as ICI. In order to avoid this, what we did at the receiver end, we removed the CP and did the further processing. So coming to the design issue, what should be the CP length? It should be greater than L. So if you have LTAP filters or L multiple paths, it should be greater than L. And the number of subcarriers, yes, N, TS equal to N times B, and TS must be much, much greater than T. As N increases, no doubt TS increases. So now to compensate ISI, this is the desirable thing, or delta F becomes much, much smaller than BC. But increasing N also increases the decoding delay of the system. Why is this? We have to wait N times N TS time in order to decode one OFDM symbol, right? Because everything is appearing in parallel at the receiver end, you need to wait for so many time, N times 1 by B, in order to do the decoding. So simply you cannot increase N. There is a trade-off. And also, as N increases, there is something called, what is it? The Doppler, right? As N increases, you cannot simply, there is some design here. Give me some time. Yeah, ideally N should be much, much greater than L, but there is an upper limit on the value of N, because we know delta F, that is the sub bandwidth, delta F is equal to B by N. What happens if N increases? The delta F or the sub carrier bandwidth becomes much, much narrower. Okay, so but this delta F must be greater than the F Doppler. So you cannot make it more narrower. Okay, so two things. Delta F must be less than the coherence bandwidth of the channel, but the delta F must be greater than F Doppler. If you simply go on increasing N to an extent that delta F becomes much narrower, and if delta F becomes less than F Doppler, that is not good, right? It becomes fast fading. So for the channel to be slow fading, this delta F must be greater than F Doppler. So delta F must be greater than coherence, less than coherence bandwidth, and delta F must be greater than F Doppler. So this is all about OFDM. There are some concepts, maybe you'll have to reason multiple times to understand. But if you have already done the course and you're all well aware of these terminologies, you can easily understand, or this will be a revision class.